Okay, exerganic and enderganic reactions. Exo, outside, endo, inside. This is about the energy. All chemical reactions are either exerganic or enderganic. So the definition of exerganic reactions results in a release of energy. Exo, outside. Right? Exo, outside. Enderganic reactions results in absorption of energy, taking inside. Absorption, to take into. Endo, absorption. Release of energy, absorbing energy. That catabolical reaction, remember that we just discussed in the previous video? Exerganic reaction is catabolic reaction, right? Because catabolic reaction, you have a complex molecule and you make it more simple. So enderganic reaction would be anabolic reaction, right? Because you're absorbing energy. You're going this way, right? So you release energy here by breaking down energy yielding bonds. Then you use this energy to put this pathway to work. And then you're storing energy back in your bonds, right? You're connecting molecules. So you're absorbing. You're harvesting, collecting, you're using it, and you're restoring it back. That's what happens on a cellular level in the human body. Not just in the human body, with the plants as well. So, exerganic reactions. Decreasing energy of the system because you're releasing energy. So there's less energy you're taking out of the system. Products, that's what's going to happen at the end. This is the product, right? That's the product. This is the reactants because you start with this. Products will have less of potential energy. Potential energy is the energy that is able to do a work. Here's the higher potential energy, here's the lower potential energy. Because I can generate a lot of force by climbing high, I can generate less force by staying at the low level, right? Because if I'm going to drop this, I'm generating more energy, and the energy kind of spills out into the environment. In the human body, we're able to harvest this energy. This energy here just went somewhere. So exerganic reaction. So your reactants have higher potential energy, and your products have lower potential energy, or less potential energy compared to reactants. Oxidative reactions, we'll discuss this later. Breaking down food when eating, releasing energy, right? Catabolical reactions by eating foods. Carbohydrates, right? Carbs made of glucose molecules, right? Reactants have higher potential energy, products have less potential energy. Enderganic reactions, absorbing energy, products have more potential energy. You start with your reactants, and now your products. This is the mono, right? So they have less potential energy, right? Here you have less, and here you have more. Here you have less, and here you have more. When you look at the products or reactants, do not memorize that products have more or less, because it could be different depending on the context. Look at what is a product look like and what the reactant look like. So the products have more potential energy than reactants, right? So your reactants have less potential energy, and your products have more potential energy because you just store the energy here, and this molecule looks bigger That's a polysaccharide, polypeptide, whatever that molecule is. Exergonic reactions. Your product have higher potential energy. Your reactants, Your reactants have higher potential energy, but then your products, because you're breaking it down, you're releasing energy, right? So now your products have less potential energy. With endergonic reactions, your reactants have less potential energy, and your products have more potential energy. But here you need energy to build energy, right? Because you have to climb. For me to climb higher and higher to generate more of kinetic energy, I'm making more of kinetic energy because I'm climbing high, I need to use a lot of energy. So I'm using this energy here in order to build this, and I'm building this energy, putting that energy back in the bonds. Energy yielding bonds. So when you eat carbohydrate, you're breaking it down into glucose molecules, you're releasing energy. But the thing is that glucose is also energy. If it would be protein, you're releasing that, you're breaking down protein into amino acids. Amino acids is also energy, even though you're releasing energy in form of ATP, let's say, and this is also energy. We'll get to this more later. And here's an example of building muscles, storing energy. Building muscles, storing energy, if this is a muscle. This concept is kind of, I wouldn't say complicated, but mind-boggling. So in this thermodynamics, part of this, so the thermodynamic, so let's look at this. The speed of chemical reactions can be affected by temperature and concentration of the reactants. More reactants, so you can speed up the chemical reactions, right? Just putting more fuel into the fire. So increased temperature usually increases rate of reaction. Concentration of the reactions, think of fuel, gas in the fire, increases concentration. So concentration of reactants, right? Concentration, number of reactants. This leads to increased so the concentration of reactants can speed up or increase the rate of reaction. Particle size, that's very important, because when we get to the fluids, the liquids, that would be very important. Remember that's just simple to memorize. Particle size, the smaller the particle, the faster it travels, and it usually increases the rate. So you have few particles, right, in the closed environment, and they bounce off the walls. Now you increase reactants, particles, they have less space, that increases the pressure, and they move highly, and they bounce from the walls, and they bounce one from another, and they want to escape that environment. So by concentrating or increasing the rate or the concentration or the number of the particles, increases the rate of the reactions. And that may increase the temperature itself. But what if you increase the temperature by fire? You also increase the movement of these particles. So the smaller particles travels faster, and the smaller particles usually increase the rate of the reaction. All chemical reactions theoretically reversible. Theoretically. Equilibrium occurs if neither a forward or reverse reaction is dominant. Energy requirements to go backwards are too high, or products have been removed. Let's skip this. Entropy and enthalpy. So how do you remember which one is which? One is a heat, another is a disorder. Disorder is the energy content of the system. Heat, I'm looking for heat, the energy content of the system, thermodynamics, whatever. So H. Enthalpy, H. H represents heat. Again, it has nothing to do with that, but it's easier to remember that. The other one doesn't have H, so that's a disorder. So the enthalpy is the energy content of the system, the whole energy within the system, closed system. A measure of the total heat, here we go, the total heat of energy in a substance or a process. Substance, closed environment, or the process creating the reactants. It includes both the internal energy of the system and the energy exchange within the surroundings, often used to analyze and quantify the heat transfer and so on. So the enthalpy is the energy that is present in the system, and that energy wants to escape constantly. We need to contain that energy by the boundaries. We're talking about the cells. The next chapter would be cellular structure, cells that have boundaries. We want to maintain that boundary. Like the skin separates external environment from the internal environment. We'll get to that later. Entropy, disorder. So this can relate to that, not can, it relates to this, because we want to contain the energy within the system, and if the energy escapes, that leads to disorder. A measurement of the degree of randomness, molecules moving spontaneously in disorder, right? So the more molecules getting inside of that closed system, so the more spontaneous they start moving that, and then may lead to an entropy that can lead to disorder. Decomposition of food, for example. So is the measurement of degree of randomness disorder in the system measure of how spread out or disorganized the particles in the system. Let's say naturally you're supposed to have 4 particles, but then something happens with the environment and you start adding more and more and more. So there's pollution, right? So you're somewhere outside, somewhere where there's a pollution, right? Gases, smoke. You're living nearby the bus depot, right? So there's gases. So those extra particles, volatile particles getting into your system, leads to disorder, randomness, cancer, destruction of the border cell wall, cancer, radicals, too much of food, too much of energy. You consume lots of food, extra food that your body does not need, that can lead, potentially, can lead to a very detrimental outcomes. Entropy tends to increase in the natural process, moving toward a state of great disorder or randomness. That's what it is. And examples so out of all that, enthalpy, heat, relates to the total energy content of the system, heat, energy, and entropy relates to a disorder, but they related one to another. More of heat, more disorder. However, naturally, we tend to go towards greater disorder or randomness.